Hey everybody, I think this is live. This is my first time using StreamYard, so hello. This is Al from Alchemy University. Super excited to see you all here, even though, again, just testing out the new StreamYard config. I'm not even sure I can see people here, but there are people behind the scenes managing all these screens and everything. But yeah, welcome everybody. So excited you're here. I'll take this slow just to make sure that more people can trickle in and get some context into what we're about to do. A couple of just quick AU updates. We are releasing week 3 content today. So expect that in your dashboard for the ETH bootcampers. And we're all really excited about this week of content. We worked tirelessly to get it to a state where it can actually teach you good Ethereum fundamentals, not just kind of keep you in guide purgatory. But yeah, welcome guys. So excited you're here. If you're here, you're a champ. You're working through the content. You're in the AU Discord. You're becoming involved. That's exactly what we're looking for. So thank you all so much for being so involved. I will introduce kind of what we're about to do. So Jacob is going to be the instructor on this live stream. Jacob was one of the OG ChainShot instructors. He's amazing. He's the best guy ever on the planet. Incredibly smart and incredibly well informed on these topics. So he's going to be doing like a general overview of week 3 content, or week 2 content. And just to recap the week 2 flow, week 2 started us off with comparing and contrasting the account model that Ethereum uses to keep track of user balances with that of Bitcoin's, which is the UTXO model. And then we moved on to a module where we started looking at trees just as data structures, just general tree data structures, which led us into the next to last module, which is Merkle trees. And basically how Merkle trees add all these cool rule sets onto a tree data structure that makes them like super efficient for data verification and storage. Jacob will review this more. And lastly, for last week, for week 2 of the Ethereum Developer Bootcamp, we covered Patricia Merkle trees. So I bet there are a lot of folks here who were in the town hall yesterday. I am Al/Patricia now because of my love of Patricia Merkle trees. But that's the week 2 flow. Jacob will cover more into it. He'll look to review Merkle trees a little bit more specifically, just kind of break them down a little further, kind of ground us to like the concept of Merkle proofs. And Jacob will also be giving a intro to JSON RPC. JSON RPC is a big part of this week's content. So if you are not familiar with what those words mean, you should be as an Ethereum developer. JSON RPC is the lowest level API kind of bridge used in Ethereum, or a pretty low level one. But I'll let Jacob introduce that further. So without further ado, Jacob, take it away.
Hey, thanks a lot, everybody. In case you're not familiar with me, my name is Jacob Height, and yeah, I don't have to say much more. I think Al did a really good introduction of myself. So yeah, just to kind of recap what I want to go over today was, just kind of recap some of the concepts we got in week 2, and then we're gonna have a student demo by a very brave student. Bardo's here, and Bardo Molina, and he's going to be demoing his project for us. We'll bring him up on stage in just a second. And then after he demos, I saw a lot of different conversations going on in the Discord, and there's a couple themes that came up about Merkle, Merkle trees, Merkle proofs, Merkle roots, how they work, why they work the way they do, and like why we even bother with these things, right? So I kind of want to, field those questions kind of live in person with you guys. That I saw these themes coming up in Discord. And then after that, I'll just kind of go ahead and intro all the week 3 content that we've been working so hard to get out this week. So we'll kind of take it like that. Yeah, so let me just like quickly review the concepts. Particularly, I think the cornerstone concept. We learned a lot about binary trees this week, right? And the reason why we had to learn this data structure was kind of to lead up to these more complex usage of binary trees. And the next step up would be like kind of the Merkle tree, right? And that has like really cool properties that we used in the weekend project, where we kind of created this Merkle proof. We had like kind of a client and a server speaking to each other, and we were using these Merkle proofs to verify people, if a name was in a given gift list or not, things like that, right? And then like I think that's about it. We got into partition Merkle trees, which is an extension on a Merkle tree, which just kind of takes that one more level of efficiency in terms of lookups and stuff. But that's not so much what the product is about, or what the project was about. And if you know the level of partition Merkle trees, that's great. That's typically not necessarily something that Web3 developers will work a lot with. That's kind of more of a protocol level. Like if you want to work on the Ethereum protocol itself, you'll need to know that inside and out. As a dApp developer, I think Merkle trees are very, very common in terms of like airdrops and things like that. And then, so I think, we can just kind of leave it there. I think the best way to kind of learn this is let Bardo, a very brave student. Thank you, Bardo. We could have him demo his project now. And then I'll kind of go into some of the questions I saw being asked in Discord after that. So can we welcome Bardo to the stage with some round of applause? And Bardo, I'll let you take it from here.
Thank you, Jacob. Yeah, I'm so excited to be here with you today. Let me present. Okay. Can you see my screen now?
Yeah, sure can.
Cool. Thank you. So, the goal of this week's project is basically given a huge list of names. We have a huge list of names here, 1,000 names. So we want to be able to verify that any of these names belongs to the list in the most optimal way by using Merkle trees. So for that, we have two components. We have the client, where we're going to use to send one of these names and a proof to the server. And then in the server, we have to be able to verify that name actually belongs to the list, right? So for that, let me go through it. Let me open the server first. So here, what we're going to do first is we're going to take the list of names, and we're going to generate a Merkle tree, and we're going to take the root of that Merkle tree. And that's all we're going to need in order to verify that any of the names in the list belongs to the list. So for that, let me uncomment this first. Here, I'm going to call the server. Sorry, I didn't save it. Save it first.
Hey, Bardo.
So here, basically,
could you just zoom in a little bit? It's a bit hard to see from the streaming side.
Yes, sir. Sure.
Thank you.
Here, it's better like this. Oh.
Yep.
Can you see it now?
Yes, much better, much better. Thank you.
Yeah, cool. So basically what we're doing here is we're taking the list of names, we're generating a Merkle tree, and then we're getting the root of that Merkle tree, which is here. We can find it here. We're doing a console log here to print it. And this is all we're going to need in order to verify that any of the names in the list is actually a valid name from the list. So we're going to take this root here. We're going to save it in a variable in the server. And now we're going to comment this again, these lines, save it. Let me clear this. Yes, so now let's go to the client. And in the client, what we want to do is, given a name, we want to send a name to the server and a proof that we're going to generate with the Merkle tree as well. And then the server will be able to say if that name actually belongs to the list or not, just by comparing that proof with this root of the Merkle tree. Right. So I'm passing the name that we're going to send to the server as an argument to the command line. And then, so let me start it here. Node client. And then we're going to pass one of the names in the list first. Let's see, Alexander. So actually, I'm going to send two arguments to the client. The first one is the one I'm going to use to build the proof. And the second one is the name that I'm going to send to the server to verify with that proof that the name actually belongs to the list. Usually, these two names should be the same, but maybe a malicious actor, they just build the proof and then send a different name to the server. And we're going to check that as well. So for now, we're going to send the same name twice. And then we see that in the server, we're receiving the name, we're receiving the proof, and then we can validate that that name actually belongs to the list. So let me go through the code here. We're taking the first argument, we pass to the client, we're finding the index, so the position in the list of that name. And then with that index, we're building the proof required to verify that that name exists in the list. And then in the server, the request we're doing to the server, we're sending the proof that we generated here with the Merkle tree, and then we're sending the name that we want to validate as well. So let me do another test. We're going to send we're going to build a valid proof with a valid name from the list, but we're going to try to verify a different name. So let me put Alexander Smith, for example. And in this case, the server verifies, identifies that that name is actually not a valid name, comparing that name with the proof provided and comparing it with the Merkle root we have in the server, right? And here, just to show you how the verification works in the server, here is where we're receiving the arguments from the client. So we're getting the proof from the client, we're getting the name that we want to verify, and then we're calling the verify proof function that's gonna build the hash that for this proof and for this leaf, and it's gonna compare it with the Merkle root to verify that that's actually a valid name, right? So the important thing here, I think, in my opinion, is that we're just storing this 32-bit value, and with that, we're able to verify that any of these 1,000 names belongs to the list.
Yeah, that's absolutely excellent, and I really like your kind of extra security check about kind of like having the two arguments where you kind of like put a name that's in the list to build the proof, and then you kind of have like a fake name malicious actor that actually isn't in the list. I hadn't actually thought myself to do that, so I thought that was a great extra security check. So, let me ask you some questions here. Like, at the end of the day, we have all these leaves, right? And the reason I'm asking this is this, kind of leads into some of the discussions that came up in Discord, right? So we have all these leaves, right? And then we kind of hash each leaves and combine them and kind of build this tree structure, right? And we know that because of the way hashing works, it'll be like almost impossible. Like if any leaf changes, the Merkle root will actually change. So why do we actually take the trouble and the difficulty to build a tree? Why don't we just take all the leaves, concatenate them, hash them, and then we have our Merkle root? Why do we build a tree?
So you mean instead of just storing all the values in the server to do the comparison, or like?
Well, also on the server, right? All we actually have to do is store 32-bit value Merkle root, right? The 32 bits. So
right.
There's the simplest way we could do that is just to take all the leaves, concatenate them, and hash them to 32 bytes, and we're done, right? So why do we why do we bother with building this binary tree at all? It's like a lot of extra work. Like, any thoughts on that?
Right. Well, the thing is that if we did that, actually, in order to prove that one of the names in this list it's actually a valid name from the list, we would need the proof, which could be all the other 999 names in order to verify. So in this case, what we have to send to the server is just the proof, which is 10 nodes, like 10 other values in order to verify. And actually, I added some logging here to prove that. So actually here, let me run the server again. Let me uncomment this again. So here I'm adding some logging as well. So here I'm outputting, this. We have 1,000 names and we have 10 layers in this Merkle tree, and that's all the nodes that we have to include as a proof to prove that any given name is a part of the initial list. So when the client sends a request to verify, we only need I'm adding some logging here as well, actually. Yeah. So we only have to send 10 nodes to prove that this is a valid name. And that's why we build a tree and not, just has all the other names, because if we did that, we will have to send 999 other hashes for the other names, right? And this is actually, as this list increases in number, it becomes more valuable to do it with a Merkle tree, because now we have 1,000 names. But if we had a million names, we would only need 20 nodes to send to the server, right, in order to verify that the name is part of the list, actually. So as the names grow exponentially, the number of nodes we have to send grows in a linear way.
Yeah, absolutely great answer. So yeah, to kind of summarize that, I think that if we have n leaves in the tree, right, since this is like a binary tree structure, anytime we have n leaves, then to send a proof to be verified, right, is only going to be the log base 2 of n. So we get this kind of logarithmic scalability. And that's exactly why we built this tree structure. So awesome, you hit on that perfectly. And just to kind of so some of the comments and I saw in the Discord were like, I guess one of the first ones was like, so on the server, so the thing is, like, on the client, we have to build all this stuff, right? We have to build this Merkle proof. And to do that, to build the proof, we actually need all n leaves to build it, right? And as we're discussing, that's quite expensive. But why are we taking the time to do this? Like you said, who's going to be doing the verifying, right? So it's going to be the server. And although we haven't quite gotten to smart contracts yet, this is going to be week 4 where we actually get there. Typically, when we have these Merkle proofs or airdrops or things like that, what you're going to have is like a client usually talking to, a web server, web 2 server, and then the smart contracts are going to store the critical code, which is going to be the 32-bit Merkle root, and it's also going to have a verify function. And again, we're going to learn this a little bit later, but smart contract code is very, expensive to run, and it's very expensive to store data. And so that's why this log base 2 of n tree being passed to the server, and it only having, or the smart contract, and it only having to process log base 2 of n leaves, or nodes in the tree to verify that it matches its actual Merkle root. We get a lot of much cheaper verification on the smart contract side. So that was one thing. And another comment I saw was that we kind of have this maybe security fear about, everyone's going to know who's on the gift list or the invite list and things like that, right? And there was some concern about that. And I kind of went in, and I hope this explanation was clear. Most of this stuff is public on the blockchain anyway, right? So if you so I gave in Discord, I gave an example about ENS, and if you were used ENS protocol during a certain period of time, you get this airdrop. But you can go onto the Block Explorer anywhere, and you can kind of see all the ENS account addresses that were used to purchase the ENS domain. So usually the guest list is going to be public because it's on the blockchain. But and Baro, maybe I'll toss this back to you. What if we did have a guest list that we want to keep it easy for the user, right? At the end of the day, I just want to pass in my name. Hey, I'm on this list. Give me my present. do you have any thoughts about how we might do that in a kind of production system? It's very open-ended.
Yeah, you mean like without using like verifying on the server side without having to use a Merkle tree or something, like a different solution, or like a
So it's pretty open-ended. So so typically in a Web3 system, and I was just getting very open-ended there, but in a Web3 system, in a true production system, what we're going to see is we're going to have a client usually, which is going to be a dApp or a browser application, talking to a Web2 server, which is going to be communicating with smart contracts. So I think a lot of people,
so you could have a database or something on the, you could have like a centralized, like a centralized way by having a database where you can check, whether it's if that name belongs to the list or something like that. But that, I guess that could be like one option. But that would be everything could be off chain in that case.
Well, yeah. So that's where the kind of Web 2, Web 3 combination comes to really make a true Web 3 application. So still, what the critical pieces of data and functionality that need to be on the blockchain are the Merkle root and the function that does the Merkle root verification. Those two things need to be on the blockchain. Everything else could be stored in a database in a Web 2 server. So we can kind of like get away with not having to construct the proof ourselves. So we just send our name to a Web 2 server. It'll construct that proof on our behalves and then submit it to the, to the smart contract to verify it for us. So, as we go through the class and we get, more into the kind of the smart contract aspect of this, we're really going to have to focus on design decisions. Like, smart contract stuff is really expensive. The gas costs, things like that we're going to get into are going to be really expensive. So what is system critical to be on the blockchain? And what can be in a Web 2 server. And so I think that was a lot of discussion I saw come up in Discord, and I just kind of want to speak in person about that. So I hope that explains most people's questions that brought this up in the Discord. And so awesome, Bardo. I just want to say thanks a lot for your bravery coming up here and demoing your project. It was excellent, and congrats, man.
Thank you, guys.
Absolutely. Big round of applause for Bardo. Like, this stuff is not easy. So really thankful for that. So anyway, guys, what we want to do now is kind of transition, and I'll just kind of give you a preview of what's coming up for this next week. So I'm going to go ahead and share my screen and kind of talk about what we're going to be looking at this upcoming week. I think it's a really fun one, and here we go. So let me present my screen. Okay, hopefully you guys can see me. And here is the university. And just kind of opening up for you guys, look at what you have here. We have a whole bunch of new content for you guys to learn and go through. I'm not going to go through this like in great depth, because hopefully that's what this is going to do for you. But I just want to cover very briefly like what's on the agenda for this week, right? So we've kind of like talked about all these cryptographic functions like hashing and these data structures like binary trees, Merkle trees, patrician Merkle trees, but we really haven't gotten into what is Ethereum, right? And so that's what this week is all going to be about. We're going to introduce Ethereum much more concretely this week. We're going to talk about proof of stake. We're going to talk about like concepts like what is gas on Ethereum and why is it even needed at all? We're going to have like a lot of different activities. We're talking about Ethereum accounts, and we have supplemental reading for you. We're going to talk a lot about how to communicate with the network, with Ethereum. So what are we going to do? Like, we're going to talk about like different ways and protocols to talk to different Ethereum nodes that are out there. And so we're going to talk a lot about that. We're going to talk about how to both kind of read from the blockchain, these nodes that are out there. How do you read information from the blockchain? But also, how do you write information to the blockchain, which is probably even more important, right? So we're gonna have a lot of activities and things around that. And then, a lot of this reading and writing and creating transactions on the blockchain is gonna, there's a very low level protocol called JSON RPC, which we'll learn a lot about this week. In case you aren't familiar with JSON RPC, RPC stands for remote procedure call, where you're basically calling a function on a remote machine. And the way that you specify what function to call on the remote machine and what data to pass it is through the format of the message that request that you're making to the remote machine is going to be in JSON format. So we'll cover that a lot. We have a lot of coding exercises and things like that. And just to note, these JSON RPC calls are very low level. They do allow you to both read and write to the Ethereum blockchain, but it's very low level. But it's really good to understand this because we're going to move up to higher level abstraction libraries that make this much easier for us. But it's really good to know those nuts and bolts in case you see some kind of a weird, JSON RPC error. Ooh, what happened? You'll kind of have a good handle on what's going on underneath the hood. And then what we're going to do, after we've really got our fundamentals down, we got a big strong grip on what JSON RPC is, we're going to intro like a pretty famous and ubiquitous library called Intro to Ethers.js, which is going to really abstract out these JSON RPC requests for us. So you don't have to think about the protocol level, but we can just say, hey, give me this account's balance, right? There's a function called get balance. Hey, give me this contract and things like that. And Ethers will, we'll go through this, spend a lot of time on Ethers throughout the course, talking about how to communicate and write to the blockchain, and also how to interact with the contracts on the blockchain. And then finally, at the end of the week, what we're going to do is we're going to use all this knowledge we learned from the week, and we're going to build our own block explorer, right? So I think that'll be a really, really fun exercise for all of you guys to do, and then we'll have the recap. So that's what's up on the agenda for this week, and I think, for me personally in this course, this week, week 3, and the next week, which we aren't there yet, but week 4 are like a really pivotal point in the curriculum. And the reason why I feel that way is, now we've kind of got the fundamental concepts down. So week 3 is all about how do we interact and speak to the Ethereum network, and how do we get information and read and write it, like I've already said. And that's really, really cool because now it's starting to get very real. We're actually talking, we're not just writing on our own local machines, but we're actually, speaking to the rest of the world. And then week 4, which we're going to get to next week, towards the end when we do the same call next week on Thursday, week 4 is we're actually going to start learning about Solidity, writing our own smart contracts, deploying them locally, and interacting with them. So I think, weeks 3 and 4 are really pivotal in this course, and makes things like start feeling really real. So I hope you guys are like really as excited as I am to get going on this week 3. And yeah, that's all I have for now. I will stop sharing, and yeah, that's about it. If there's any questions or anything else that anyone would like addressed, or Cody, anything else you would like to say, that's all I have for you guys.
Nope, I think we're good for today. Nice job, Jacob. I hope everyone enjoys week 3 content. It is now live if you haven't heard already from Jacob and me posting in the chat. So yeah, feel free to connect with us in Discord and enjoy this week's content. Get out there and learn. Peace, love, and Web3, guys. Thank you.
Awesome, guys. Have fun, guys.